So this is an attempt at connecting potential energy and work at close to the Earth's surface to what we've been studying recently, which is potential energy and work, or I guess force of gravity at planetary distances. So we're going to start off with the reviewing idea first and just take a look at some relationships we can discover. So the first piece is just to kind of talk through how we calculate lots of different things. If I'm just calculating the potential energy at some location, it's pretty straightforward for us. In this course, we just say that it's mg times h. Now, there's something implied with that, that h is really h above some reference point, because potential energy is not something we can measure as an absolute. There's not a location has a certain amount of potential energy. A location has a certain amount of potential energy in reference to whatever you're calling zero potential energy. So as an example of this, if I have a table and I hold a ball above that table, I could say that the potential energy of this object is mg times h, where h is the distance above the table. Or if I choose to use the reference point as the floor, then I've got a different mgh. I'd claim that's a totally different amount of potential energy. Is it really? No. All that we're saying is that compared to whatever I'm calling zero, whether I call the floor zero or the top of the table zero, I have a different amount of potential energy compared to there. So potential energy is not an absolute. It's really a difference in potential energy between two places that we're always looking at. That's key point number one with potential energy. Okay, other things about potential energy and connecting it back to work. When we talk about work, we have two different ways we can express work. If we have a constant force, we can say that work is F dotted with some displacement. Okay, and the dot product says we only do work when this force and this displacement are parallel to each other, or we only do work along the portion of this path where the force is parallel to it, or we only use the portion of this force that's parallel to that path. The idea is that we need parts of things that are parallel to each other. If we have a constant force, we calculate the work done that way. If we have a varying force, what does that look like? How do we calculate how much work is done? Okay, some people made some gestures from the back of the room. I think this is what they meant. That it's F dotted with dx, that you're looking at how much force is applied over each little piece of distance, and you're adding that up. Mostly they just made like squiggles with their finger trying to show integral symbols, so I think that's what they meant. Okay, that's fine. One of these two is a more universal idea, as in this applies whether your force is constant or not. This only applies when your force is constant. What we also talked about were conservative versus non-conservative forces, and gravity was our big example of conservative forces, or of a conservative force. So we looked at the idea that when I hold the ball up here in the air, it's got some mass m, and I let it go so that it falls down towards a table or the Earth's surface or something, that gravity is the only force doing work on this object. And so when it's doing work, since it's a conservative force, what is it doing with the mechanical energy of that system? Okay, it's changing, since gravity is conservative, it changes the form of the mechanical energy, not the amount of mechanical energy. Okay, tying this idea and this idea together, we could say that if I have this mass and I drop it this way, gravity does work along this path. If I have this object and I move it sideways this far, did gravity do any work on that object? No. If I take this object and I have it go from A to B versus A to C, in which path did gravity do more work? A to B or A to C? Don't say that out loud. I guess you can say it out loud to yourself if you're watching at home, but where does it do more work? Answer that question, then we'll talk about it. Okay, so the class that we're filming this in front of was not tricked by my trick question attempt. from A to B or A to C, it's the same amount of work. And the way that Brett just said perfectly as he explained this, he said, well, because the vertical displacement is the same in both cases, A to B versus A to C, and the force of gravity only acts vertically, so the work done A to B versus A to C is exactly the same by gravity, if we're looking at the work done by gravity. Okay, the other thing we could look at with this is the fact that the work done by gravity, which would be m times g times that change in x, where the mg and the delta x, where I'm calling this displacement delta x, is exactly equal to, but has the opposite sign of, the change in potential energy. Okay, if I go from here to there, the change in potential energy is mass times g times change in height. But that change in height, I would say, is a decrease in height of so many meters. This is a negative mg delta h. This is my change in potential energy. This is my work done by gravity. The piece to tie together there is that the work done by a conservative force is always equal to the opposite of the change in potential energy. So if this comes out to be a negative number, if I multiply it by a negative, I get a positive thing. That's what we're saying there. Okay, all these ideas are exactly the same thing we're going to do, only now we're going to do it with a force of gravity that changes with planetary distances. Okay, the only other thing I have to throw in there is that your book uses some interesting notation, and the AP course uses some interesting notation. We've always used PE for potential energy. It just seems kind of natural. Lots of books and lots of AP tests like to use U for potential energy. Why? Because as the terrible pun goes, you have lots of potential. What? So bad. But okay, just go with it. It'll help you remember it. So because you have so much potential, you can also be potential energy. All right, I'm going to pause for a second and we'll go on to the planetary distances part. All right, well, we're at the end of the bell, so I'm going to pause or stop this video, and then we'll do the second half of this, like now what happens when we're at situations where gravity doesn't stay constant, so the much bigger situation in the next video. So you got a second video on the way.